In this video, I will guide you through a problem in Smith's Organic Chemistry. I'm Stoddard, founder of Study Chem, the place for students to turn for higher grades in OChem. Let's get started. In this problem, we're supposed to show how a 1,2 shift forms a more stable carbocation, and we're given these different intermediates. You want to take a look and classify the starting carbocation as primary, secondary, or tertiary. So here, we'll dot the carbocation, and it's bonded to 2 carbons. So we call that a secondary carbocation. Okay. And what we want to do is locate a more substituted carbon next door. So this carbon is a tertiary carbon, and we have a tertiary hydrogen attached to that tertiary carbon. So what we can do is we can show how this hydride here, the hydrogen with the lone pair of electrons, is going to migrate over to this dotted carbon. In so doing, let's redraw the starting carbon skeleton, and what we're going to get is the positive charge here on the left carbon, and now this is a tertiary carbocation, which, as you know, is more stable. Okay, let's repeat the same process here. Let's dot this carbon here, and we can see how starting out it's a secondary carbocation. Let's see if we can locate a tertiary hydrogen next door. Over here, these are just secondary hydrogens, but this hydrogen here is a tertiary hydrogen. So let's take these bonding pair of electrons along with the hydrogen and move it over, and what we'll get is a cyclohexane methyl group, and we'll have the positive charge now at the tertiary carbon. So we call that a tertiary carbocation, which is more stable. Okay, let's repeat the process here on this one here. Here, if we look at, again, let's dot the starting carbocation, and we can see how this is a secondary carbocation. Okay, and let's look next door and see if we can find a more substituted carbon. This carbon here is secondary. This carbon here is quaternary. So it turns out we can have a methyl shift. So the methyl, along with the 2 bonded electrons here, can migrate over. And this will give us, after reaction, a 6-membered ring. We'll have the CH3 now bonded to the top carbon, and we'll still have this CH3 bonded over here. And in this case, we'll have the positive charge located on this carbon here next door, and that's a tertiary carbocation. Okay. I don't think the authors envisioned us thinking about this, but one other possibility for C is to take, again, our carbocation, which is secondary, and we'll draw a methyl group and a methyl group coming off that carbon. Now, carbocations can rearrange by hydride shifts like in A and B, or in alkyl shifts like we saw in C. Now, what we can envision happening here is that this bond right here might actually migrate over, and what that would give us is the carbon skeleton would look a little bit like this. Let me redraw carefully what I have before I redraw it in a nice fashion. So this bond that used to be here would move over to here. Okay, move over to here. And in so doing, let's think about where that positive charge would go. It would end up onto this carbon here. Okay, so that would be a tertiary carbocation. Let's clean it up and take a look at what that structure looks like. So we have a 5-membered ring. Okay, and attached to the top carbon here, we have what looks like an isopropyl group, and there would be a positive charge here. Okay, so that's also a tertiary carbocation. But again, the authors probably weren't expecting us to think about that, but that is another possibility. Okay, thanks for watching.